Good afternoon, everyone. Welcome to Chase Plastics Chase the Knowledge webinar on understanding polyamides. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your busy day to attend. A few quick housekeeping items before we begin. This is a new format for us. If you have attended a previous Chase the Knowledge webinars, this probably looks new to you, even though it is still in GoToWebinar. There has been some changes, so it may look a little bit different. Everyone except the presenter is on mute and will be for the duration of the webinar. But if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar, which is in the upper right-hand corner now. It's a box that has a question mark on it, and that's where you can type your questions. If you have rather a lengthy question that you would rather ask verbally, you can also raise your hand in the toolbar and I will unmute you. Where you'll find the raise your hand is down in the lower left-hand corner, and you'll see a little hand there. And if you click on the arrow, you can click on raise my hand. And then I will unmute you and ask you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, and information on our technical engineering team in the handout section that you'll also see at the upper right-hand corner. It looks like a document with a paperclip on it. You can find all of the handouts there. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please just reach out to Andrea Kendrick via email or myself, and we can help you arrange that. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page. You can see the button there where you can now subscribe or invite coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars. Another great resource, technical resource, is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. Can you believe it? We are only 47 days away from the biggest show in the plastics industry, NPE. We invite you to use our code to register for free. Yes, you can still register for free if you use our code, and to stop by our booth to play Plinko. And we hope to see you all there. In addition to our presenter, Andrea Kendrick, who I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to help Andrea field questions today. And at this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. So without further ado, Andrea.
Hey, good afternoon, everybody. So today we're going to talk about polyamides. Okay. So our agenda for today, we're going to do a brief overview, kind of talk about what polyamides are. We're going to talk about making them. Not going to get crazy into the polymerization of them per se, but go over them a little bit. We're going to talk about their structure. We're going to talk about polarity, and then how that affects stuff like moisture absorption, We're going to talk about thermal performance. We're going to answer the ever existing question of 6 versus 6,6. And then we're going to go over some of the more common ones that we talk about throughout this presentation, and then kind of go over maybe some of their applications that they're well suited for. Okay, so overview on polyamides. So polyamides are semi-crystalline thermoplastics. They are characterized by great chemical resistance, specifically to automotive oils and greases. They're used very heavily in the automotive market for that reason. They have great wear performance, so used alongside stuff like acetal when we talk about wear parts, and then also great heat performance. There will be variations of performance across polyamides, so keep that in mind. Some perform better with wear, some perform better with heat, and so on and so forth. So we'll talk about some of the different ones and the common ones, but overall, polyamides tend to perform pretty well in those areas. So what is the term nylon? So we hear nylon all the time. People use nylon instead of polyamide more commonly. So nylon itself was a term that was coined for polyamides by DuPont in the 30s. Specifically, their 6,6 that they created and started making it. Though they never trademarked it, they did coin the term nylon. Many suppliers and manufacturers of polyamide today are very specific about not using the term nylon, specifically because DuPont was the one that coined it. And so most of the time, if you're looking at other suppliers, they tend to use the term polyamide, which is the chemical name for it. It's not the slang term for it, if you will. So same with POM when we use acetal, or we'll say PMMA or acrylic, kind of one of those things where it's a slang term for it. But most of my presentation will be polyamide. You will see the occasional nylon in a picture, but do know that they're referencing the same material. Okay, so making of polyamides. So there's a lot of different types of polyamides. So there's one of two techniques that are used when we go to create a polyamide to make a nylon. So the first one would be if we're making a double number polyamide. So this would be your 6,6s, your 4,6s, your 4,10s, your 6,12s, you name it. If it's got two numbers, generally you use a slash to distinguish that there's a difference. Sometimes they'll use a comma, but if there's two numbers, what we do is we take a diamine and a diacid, and we use those to create those polyamides. Di meaning two, so you've got an amine and an acid used to create those specifically. Now, when we make our single number polyamides, we do what's called ring opening. And so basically think of a benzene ring, if you want to dig back deep into our chemistry background. Basically, your 6 carbons in a ring, cut it open, string it out. It's a very simplistic version of that. And then the different rings for the different amounts of carbon needed to make your 6, your 11, your 9, your 10, your 12 nylons. So what I want to point out here, though, in this picture is when you take an amine group, in this case, your NH group. I did also put under there, if it makes it easier to remember, an amine has an N in the name. So NH is the amine group on the backbone of a nylon. And then an acid group with a C in acid, C double bond O, if it makes it easier to remember. If you take an amine group and an acid group together, they make an amide group. And so that's where the term polyamide comes from. Poly meaning many, many amide groups. So these will repeat, and you will see as we talk about some of the structure in the coming slides, that's where the name polyamide comes from. It's an amine and an acid group together. Okay. Lots of very fancy chemistry words on this one. So when we talk about, again, single digit being ring opening, you can see in the column off to the right-hand side, I put what reaction type we use, ring opening or diamine and diacid. So stuff like a polyamide 6, PA6, caprolactam is used for the monomer there, ring opening. And then when you use your 2 number nylons, PA66, you have hexamethyldiamine and adipic acid. So HMD and adipic acid for PA66. So when you hear things like there's a shortage of HMD or adipic acid, that's why it then ends up resulting in issues with getting PA66, or maybe an issue with caprolactam. It could be an issue with getting 6. And then some of the other ones you'll see down a little bit further, stuff like your 610 and your 612, you can see that they start with the same diamine, HMD, and just use a different acid. That's why companies like Ascend have had less of a problem jumping from producing 6,6. They were already using HMD. They just had to switch it out for a different acid to make those new nylon grades materials. Okay, so the actual structure itself now. What do the numbers mean? How do I read it? What does it do for me? So when we go to look at a polyamide grade, the number that's there, 6, 6, 6, 4, 6, whatever it is, the numbers will tell you the number of carbons between the amide linkages. So our single digit one, you're gonna have your amide group together on the backbone. Again, over here, C double bond O, it's your acid. NH, your amine, and acid makes an amide group. So here's your amide group. And so to get the number, we simply count the carbons on the backbone. So we've got 1, 2, 3, 4, 5. And we do count the carbon that is in the acid group because it is also on the backbone. So you count 1 through 6. This is a polyamide 6. This is what the chemistry looks like for that. If it was a 12, you'd have 11 of these CH2 groups and then the C double bond O, and then a 9, a 10, so on, so forth. This is exactly what your 6 looks like when you're referencing it. It's its chemical structure. Slightly different to that, only slightly.
Andrea, I'm sorry to interrupt, but your mic is cutting out a little bit. I don't know if you're moving it, but it's starting to kind of fizzle out. Andrea, you still there?
It turned my mic off. I don't really know why.
Okay.
Good. You can hear me now though?
Yeah, you sound better now.
Okay, good. It muted me for some reason. I'm not entirely sure why.
All right, you
Okay,
sound good now.
so do I have to go back any of them? Did it cut me off during any of the last
Maybe
slide?
just start at the top of the slide.
Okay, thank you. Apologies. Okay, so now when we talk two number nylons, this is where you're going to see a little bit of a difference because you have your two amines and your two acids with your amide group kind of in the middle. And so again, NH, amine, C double bond O, acid, together is your amide group. When we do a double digit now, what we're looking at, or double number, I should say, the first number is going to be the amount of carbons between the amine groups. So you can see separated here, NH, NH. To get the first number, I count the carbons between that. So this, in our fun chemistry class, if we go back far enough for it, means that this group is repeating 6 times. So there are 6 carbons here. So the first number in this particular nylon is a 6. Then the second value, your Y value, is going to be your number of carbons between the acid groups. So C double bond O, C double bond O, and then this repeats 4 times. So this is 4 carbons. And again, we repeat and count the ones that are on the backbone within the acid group as well. So 4, 5, 6. So this is a nylon 6, 6. And then down here, same thing, slightly different way of writing it out, but we've got 4 repeats of the CH2 groups. So that's 4 carbons. So I know that this is a polyamide 4. And then I count the back section as well between the acids. 4 carbons, repeating, carbon, carbon, 6. So this is a polyamide 4, 6. Now, if this was a 6, 12, this would repeat 10 times, and so on and so forth. And so all I'm doing is counting the number of carbons in the backbone between my amine and acid groups when I do a double digit. Okay. All right, so what does that mean, or what does that do? Seeing that the makeup is all the same, the only thing that differs is going to be your amount of carbons. So what does it do to the actual nylon itself? What does it do to its performance? Well, what happens is the oxygen, as part of the acid group, has a slightly negative charge, a partial negative charge. And when we talk about the hydrogen that's part of the the amine group, it is a partial positive charge. So those two on the backbone of the nylon are actually attracted to one another. So what ends up happening is they attract one another and they form a hydrogen bond. And so the H, partial positive charge, partial negative charge on the oxygen, they're attracted to one another, they form a hydrogen bond. Now, the greater or lesser amount or overall density of these hydrogen bonds that occur within the makeup of the polyamide, that's going to start to affect its overall polarity, crystallinity, and affinity to be attracted to water, because water is also polar. So the more hydrogen bonds you have, the more occurring that they are, the more attracted to water they will be. And we'll go over that a little bit with some data in the following slides as well. But that is why nylon reacts the way it does. We know that it has an issue with moisture absorption. This is why the hydrogen bonds that are created between your oxygen and hydrogen molecules. Okay, so nylons and moisture. And so going back to the page before, the greater the frequency of the amide groups, again, the amine and the acid groups together create an amide group. So the more often that they occur, meaning the shorter portions of carbon that exist, or the lower number of nylon it is, the greater the water uptake is. So and then the reverse side would be as I increase the chain length, so there's more carbons in it now, so 12 versus a 6, you end up with a decrease in water absorption. And so what does that look like from a value perspective? We have the different nylons listed out. These are the common ones that I'm going to talk about throughout my presentation. But if you look at a 12 carbons on the backbone, longer chain nylon, you're looking at 0.7 for absorption at equilibrium. Now, if I jump to something like a 6 or a 6,6, where there's 6 carbons instead of 12, so half as many, it jumps to 2.8 or 2.5. And then even further still, if I lose just 2 carbons on the backbone between a 6,6 and a 4,6, I jump up to 3.7% at equilibrium. So longer chain ends up being lower moisture absorption. Shorter chain, more moisture absorption. So moisture absorption, in the realm of speaking about that specifically, I wanted to address something that we get asked for kind of often, and that is, can I get melt flow data for my polyamides? The reason we typically do not provide that is because the material itself being so affected by moisture, that starts to affect the data that you're going to receive. So in this graph here, you can see it's the same material at different moisture contents. You can see that you get different melt values at the different moisture contents. Again, all the same material, it likely has the exact same, it's gonna have the exact same viscosity if you tested it another way. But if I do a melt flow test, MFR, you can see that if I'm down at a 0.05% moisture, which is kind of where we want you to be when you go to run it, you're at about a 10.5 melt. If it gets all the way up to 0.2, still within the realm of the range we'd like to see you in for processing, and generally a max for what our suppliers will provide us, it jumps all the way to a 14.5. So this, as you can imagine, it's all within the realm of acceptable moisture content, but I've jumped over 4 on my melt flow just because of that change in moisture. Now imagine it's been sitting for a little bit and maybe it's at 0.3 or 0.4% moisture. Or maybe we've dried it even further past 0.05 and maybe it's 0.01. The range of values you would get for testing it are going to be all over the place. And if we were to try to do melt flow data, we would want the drying or the moisture content to always be the exact same. So that's not a variable within it. And that's hard to do. If you've looked at the testing you received for lots of nylon, it's going to come in that range. As long as it's under 0.2 is generally the max that our suppliers will provide for us. As long as it's under that, they're okay. But they're going to vary. And so getting a melt flow test on that would vary It's why we don't provide melt flow testing for nylon. What you will get or can get though is relative viscosity or viscosity number testing, because then it takes all of the moisture out as a variable. So keep that in mind if you're being asked or you get ready to maybe ask us about melt flow testing. It's highly unlikely that we're going to have it or get it, specifically because nylons are so affected by moisture. Okay, so now we're going to talk about nylons and heat performance. So we just talked about how the structure itself and the hydrogen bonds affect moisture. They also affect its thermal performance. So the greater the frequency of amide groups, again, my amine and acid together on a backbone, the shorter the carbon chain. So there's more amides, means there's less carbons happening. There's more hydrogen bonds that are existing and more hydrogen bonds that need to be overcome to melt the nylon, meaning it's going to have a higher melt temperature. So flip that. If I increase the chain length, so now I'm at a nylon 12 versus a 6. If I have more carbons in the backbone, longer chain, Pa12, it equals a decrease in the amount of hydrogen bonds that exist, which equals a decrease in the melt temperature. So longer chain have lower melt points than shorter chain nylons do. And that data is kind of provided here as well. So if you're at a nylon 12, which would be kind of the longest ones we tend to see or work with, as a melt point of 176 C, then I drop down to a 6.6 and it jumps all the way up to 250 degrees C. It's a pretty good swing. And then again, just 2 carbon difference to a Pa4.6, it jumps another 45 degrees up to 295 degrees C melting temperature. So my longer chains pick up less moisture, but are lower heat than my shorter chain nylons are. And so a lot of times you'll hear people refer to your 10s, 11s, 12s as long chain nylons, and then short chain would be your standard 6.6s, and then even 4.6s would be part of your short chain. The other term you might hear as well would be linear, because there are aromatic, partially aromatic nylons that exist out there. So you might hear someone refer to these as linear nylons as well. So keep that in mind if you're kind of hearing that term floating around. They just mean your standard linear ones that are non-partially aromatic. Another way to look at that temperature performance would be something like this is a shear modulus versus temperature. So again, just a couple carbon difference. You can see that your nylon 6 starts to drop off and lose its stiffness at a temperature quite a bit lower, and then completely fail by 200 C versus the 4.6, which performs out to about 280-ish C. So again, just a couple carbon difference, but just enough for those hydrogen bonds and the crystallinity to take effect and end up giving you better heat performance in your 4.6 versus a 6. Okay. The question that we probably get most often when we talk about nylons now is going to be 6 versus 6.6. They're very similar in the amount of carbons, 6 of them, between your groups. So overall, what is the difference? What do I say is a big enough difference between them that I'm worried about it? So the first thing to know is that although structures very similar, 6 carbons, 6.6 does have more hydrogen bonding, resulting then in a higher melt. And so more bonds, higher melt, higher temperature it has to get them to melt and break apart. 6.6 is the higher heat of the two. 6.6 also crystallizes into a different crystal structure than 6 typically does. This also then affects its rate and the amount of crystallization that 6.6 has. And so these will play out when we go over the next couple slides, giving you kind of a little more example about it. But the structure that it gets into also affects its performance. Okay, so for 6 specifically, where would I use it? Where is it better? 6 is better subjectively, and I say this because not everybody wants a glossier appearance or finish. Subjectively, 6 gives you a better surface appearance, especially in the glass-filled grades of 6, because it hides the glass better. So you get a smoother, glossier finish when you use a PA6 versus a 6.6. You also process it at a lower temperature. It has a lower melt than 6,6 does. Therefore, you process it at a lower temperature. This then helps if you're going to do anything after the fact or maybe a secondary operation like welding. So when you weld or when you overmold, because you have to get the surface to melt again so you can get it to either stick to itself when you're welding or get a TPE, some variant of a TPE to stick to it. You have to melt the surface of it. So if it's a lower temperature material, you have to get it to a lower temperature for it to melt to then weld or overmold. So 6 is preferred in those applications. And then lastly, another really good point is that it shrinks less. And so you end up with lower likelihood of warpage. And so warpage being differential shrink, so shrink in different directions being different. You get lower likelihood of that and lower shrinkage in a 6 versus a 6,6. So approximately 10 to 14 thou shrinkage versus your 6,6, which is closer to 20 thou inch per inch shrinkage. So better surface appearance. Again, I say subjectively, if you like to be shinier, that's for you. So better surface, lower processing temperatures, which makes it better for secondary operations, and then lower shrinkage and lower likelihood of warping. Now for 6,6 being a higher temperature material, as you can expect, one of the advantages is going to be that it has a higher heat performance. If you are over 200 C, you would have to look at using the 6,6. If we go back and reference the graph that I just showed, that was a 6, fell right off at 200 C. So anything above 200 C, you have to go to a 6,6. Anything below 200 C, you might be able to consider a 6. So higher heat performance for a 6,6. The other thing is that a 6,6 is better in water or glycol if it is seeing extended temperatures above 120 C. So if it's going to get hot and there's going to be water around or glycol around above 120 C, you have to use a 6,6. So just standard heat performance and it's not seeing water or glycol, 200 C plus, we have to do 6,6, 120 C plus if it has water or glycol resistance needed. So maybe an automotive spec where they've got quite a safety factor, but if it needs to test above that and still perform, we have to go 6,6 versus 6. And then lastly, talking about the crystal structure again for it, it cycles faster, which means it's going to crystallize faster than a 6. So when unfilled grades of 6,6 will crystallize about 12 times faster than a 6. And then once you fill it with glass, it's about 3 to 4 times faster. So if you're making parts that are high cavitation, you're making a lot of parts in one shot, and you're trying to do it quickly, 6,6 is going to be the option for you. And keep that in mind then, when sometimes we have shortages of 6,6 or 6, if you're making parts that have to cycle quickly, you're making a lot of them in one mold, you might have a really difficult time attempting to offset 6,6 with a 6 in those applications. Okay, so now we talked about 6 versus 6,6, talked about structure a little bit. Now we're going to talk about each individual one, the main ones that we were discussing, and some of the applications that they're good for with a little bit of tips, as well as there's a table. All of these following slides are formatted the same. They have the table with information in them, so you can quickly compare to the other nylons as you're scrolling through. So first one up is going to be your nylon 12. It is a longer chain, making it more flexible, but it has lower heat performance because of that, as we mentioned, but it also has lower moisture absorption than your shorter chain 6 and 6,6. And so you'll notice as we go through, tables will be there, but your moisture absorption being at 0.7. And then I provided shrinkage as well as tensile modulus. So you can get an idea when we say that it's a little more flexible, the stiffness will be lower. And so your tensile modulus will be lower in these grades versus your shorter chain 6 and 6,6, which you'll see as we get through these slides, it'll be lower value. So tensile modulus on a 12 is about a 1400 MPa. And so maybe keep that in mind as we go through the next one. So some applications for polyamide 12s. Tubing is a big one, a little more flexible. So a lot of tubing options. Cable sheets, catheters, control valves, quick connectors. Very common for PA12s. Used quite a bit there. Again, more flexible, not moisture, not picking up a ton of moisture. Good options there. And you don't really need heat requirements. So these applications, of course, are not requiring the heat necessary that you might need out of a 6 or 6.6. Okay. Now we'll talk about 612 briefly. So you'll notice our tensile modulus has increased a little bit. So 612 and 610, which we'll talk about next, because it has a longer and shorter portion of its chain, you're going to get heat performance, flexibility, and moisture absorption that kind of falls somewhere between the two because you have kind of a piece of both of them. And so you're going to get performance in between them. And so our tensile modulus was 1400 for the 12. It's 2200 for the 612. So it's gone up because it's getting closer and less flexible, more like a short chain. Again, kind of falling in between. Some applications that are common for this material would be monofilament, fuel connectors, solar cable ties, covered conduits, tubing. Again, tubing is a big one. This is something where maybe because of its performance being in the middle, maybe for a 6, it's picking up too much moisture, and maybe for a 12, it's too flexible or doesn't quite have the heat performance I need. This gives you something in the middle that can meet both of those requirements. Okay. Polyamide 610, similar to the 612, you're going to end up with heat, flexibility, and moisture somewhere between the two again. So pretty close actually to the performance of the 612. Your 610 is about 2000 MPa. So we started at 1400 for the 12. We went to 2200. We're at about 2000 for this one. So kind of in the middle, which you'll see is, we get to the 6 and the 6.6. The other thing that's nice about the 610 is that it also contains bio content. So maybe I'm looking for something in the middle for performance, maybe less moisture absorption than a 6, but higher heat than a 12. But then I also maybe need the sustainable solution portion of it. Maybe I need it to be a little green. So the 10 portion of that nylon is bio-based. And so could be a good option for a application that needs something like that. So common applications, again, monofilament, fuel connectors, thermostat housings, coolant valves, stuff that we can stay in the automotive realm because nylon in general, again, good with automotive fuels, gases, and then maybe we just don't quite need the heat that the 6 and the 6.6 offer. And so we could potentially squeeze a 610 or 612 into some of these applications. Okay, so now into 6. So again, all the way back to the 12, 1400 MPa for stiffness. Then we went to about 2200, 2000 for the middle ground, 612s and 610s. Now at 6, we're at 3200 MPa. So stiffer material, less flexible. So 6, as we mentioned, it hides the glass better, has lower shrinkage, and can be processed at lower temperatures compared to a 6.6. But then it's also higher temperature, but also higher moisture absorbing than our long chains, 12s. But it's good for overall overmolding applications. If we're going to overmold onto it, it maintains that it's a good option for that. So some common applications, clips, firearm grips, maybe we're going to overmold TPE to the bottom of that, best option for that. Fan shrouds, handles that might be part of an overmolding assembly or part, stuff for handles on chainsaws, maybe your exercise equipment, handheld tools, we're going to overmold the grips onto it. Easier to do with the 6 versus the 6.6. Then we have our 6.6, which as we also mentioned, faster cycling, higher heat compared to 6, making it ideal for applications that need the high heat and or high cavitation tools that need the faster cycling time. So tensile modulus about the same, 3200-ish. So again, quite a bit better and less flexible than your 1400 that you have with the PA12, and higher heat. So now our melting point of 6.6 is up to 250, where the 6 was only about 218. So as we mentioned, higher heat material than 6. So some common applications could be zip ties. Maybe we're making, we have a mold with tons of cavities in it, so we could use 6.6 for that, cycle it quickly. Radiator end tanks is a big one. Ball bearings, air ducts, engine covers. a lot of under the hood applications 6.6 fits into because of the heat performance. We will say that you can, in some of these applications, also use a 6 for under the hood. We just more commonly here in the US tend to use 6.6 because our friends at DuPont made the 6.6 and kind of spec'd it everywhere. So we use 6.6 pretty commonly, but 6 also in some of these applications could also be a fit. So keep that in mind. Seat parts for office furniture, again, a 6 could also work, specifically if you need the better appearance, but office furniture parts, caster wheels, a lot of under the hood and furniture type stuff that can use the 6.6. And specifically, if you're making ones like the ball bearing zip ties, high cavitation, we need to cycle it quickly. Okay, and then the last one we're going to talk about briefly, maybe a little lesser known, people aren't as familiar, but a polyamide 4.6. And so this is going to be the shortest chain of the ones that we talk about. So it's to be the highest temperature. It also has about double the crystallinity. So overall amount of crystal structures within a 4.6 is double that than a 6 and a 6.6. This results in superior heat. So if we look at the melt point, 295. 6.6 is 250, so we get, again, 45-degree swing on melt temperature for it, so higher heat, and then better wear and friction performance. And so we already know that nylons are used in applications for wear and friction, but stuff like a PA 4.6 has superior performance, specifically in places where you have higher pressures and higher velocities. So if you're pushing it hard or you're trying to get to move really fast, a 4.6 is could be an excellent option for that. With the downside, as hopefully we're starting to connect the dots, shorter chain picks up more moisture. So as you can see, 3.7% picks up a lot of moisture, but it's high heat, great for wear and friction applications. So in that realm, our applications would be stuff like gears, thrush washers, connectors, modular belting, stuff like in the picture you'll see, maybe it's in for food, something that might go through an oven and it needs to withstand that temperature but still wear really well. And so great for belting, stuff like that. Thin walled bobbins, high temperature kitchen utensils. Again, higher temperature, better wear performance out of a 4.6. That's all I had for you guys. If you had more specific questions or wanted more specific examples, we'd be more than willing to do that. But that is what I had to present to you guys on, specifically on polyamides, linear polyamides. Maybe in the future we can do an aromatic one, but for linear polyamides. But at this time, I will send it back to Sherry and see if you guys have any questions for me.
Great. Thank you, Andrea, for your comprehensive presentation as always. So as Andrea said, at this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. We have Jason Merkel, our technical manager, who has been with Chase Plastics since 2012, on hand to assist Andrea with questions today. As a reminder, as you type your questions, please complete the survey at the end of the webinar. Those really help us to shape our future Chase the Knowledge webinars and topics. And we always welcome your feedback. Be sure to check out our blog page and our webinars page for any future webinar announcements. Again, you can register there to receive notifications about any webinars as soon as they are posted. And also, again, if you would like to have a custom Chase the Knowledge topic presented to your organization, please reach out to Andrea. Her contact information is here, her phone and her email address, and she will be happy to help you arrange that. So Jason, I'm going to hand the questions over to you. Can you see all of them, or?
Yeah, I got them.
Okay, awesome.
All right, Andrea. First question, why does it seem some polyamide suppliers are reluctant to proactively supply the moisture content / melt flow rate curve chart that you shared? Why are they hesitant to provide that on the technical data sheet?
Well, so the chart itself or the graph itself wouldn't be on the data sheet anyway, but they are unlikely to provide it because most of them do some form of viscosity testing. So again, either the RV or the VN to provide to let you know how it's going to flow without doing melt flow, because the moisture being an issue, it's something they don't do. And so they'll give you viscosity. It's just going to come in a form that maybe you're not as used to. So it'll come in either viscosity number, VN, or relative viscosity, RV. Similar with polyesters, PBTs, PETs, similar concept. Because moisture affects it so heavily within even just the same exact lot of material, they just don't provide that.
I'll go one step further than that, even to say that I don't know that every manufacturer has even gone through a study to be able to provide that form of data. To Andrea's point, typically they have that viscosity testing on hand, so it's deferred to for that reason. But in addition to that, depending on the different types of moisture analysis done, whether it be a traditional weight loss method or Carl Fisher titration, you could have two products that theoretically have tested at the same moisture that still have different flow rates. So because there's not necessarily a direct correlation between the melt flow rate and the moisture content, they may be hesitant to publish such data. And then the other big variable with nylon so often being used in a reinforced form, that further exacerbates the issue with melt flow testing, that, in the lack of a shear environment of a melt flow test, the reinforcement can change how the outputs look compared to a true viscosity or injection molding base setting. Let's see here. Why is polyamide difficult to be UV stabilized compared to other resins, specifically nylon 6,6?
Well, not sure which ones we're comparing to specifically, but different bonds within materials have different activation energies that are attacked by UV rays differently. And so you can stabilize 6,6 and 6 and some of them to be okay in the material in UV exposure. There's just some materials that are going to outperform it. You've got materials like your ASA, your acrylics, they're just going to be better with UV stability and UV light compared to nylons. So we do our best, and there's options for UV stabilized grades, but it's just inherent of the chemistry of the material that some will be better than nylon.
And then Raphael, on that question specifically, if there's any instances that you've seen in the past where you'd like us to take another look at UV stabilization of nylon 6,6, there are options out there, whether they're stabilized via higher carbon black percentage or a hinderedimine light stabilizer. It's not a one size fits all, depending on the mechanical performance needs or the cost target for certain nylon materials, but there are options out there that have been proven to last 10 plus years in high UV settings and able to be used successfully. So please feel free to get in touch with me or your account manager after the fact, and we'd love to take another shot at it. This question was answered internally already, but just for everyone's knowledge, the question was asked is if the presentation is available online or available for reference afterwards. The short answer is yes. You should receive an email before the end of the day with a copy of the presentation and handouts, and also a separate email with the recording, and then it will also be posted on our website for future reference. And then, as always, you can get in touch with Andrea, her contact info here on the screen, if for some reason you don't receive it, and we'll get it to you as soon as possible. Can you rate the polyamide ranking for zinc chloride, assuming zinc chloride resistance?
In terms of your short chain ones, not necessarily. The long chain ones do perform better in terms of zinc chloride resistance. So your 612s will outperform 6,6s. Ascend specifically has done some testing on that because they have both materials, but it is shown that the 612 will outperform a 6,6. Now for 4,6 and straight 12, I don't necessarily have that answer. I'd have to imagine that the 12 would perform pretty well as well. But for 4,6, I do not have that information.
Andrea, you mind taking note? We'll get back to you afterwards with the full ranking as well to give you a better idea, of what that looks like.
Yeah, and there's data too that exists that could be shared.
All right, next question. Is there any relation between length of the chains and weatherability performance? And also, is there any relation between cost and the length of the chains?
Yes, to the second part for sure. For UV performance, the length of the chains, it's a great question. I think overall it is how nylon will perform. I don't know the ranking for UV, short chain versus long chain. It's a good question. We'd have to try, I'd have to find some data on that. Cost wise, it would go your more standard 6s and 6/6s, and then it would go to your long chains and your 4/6s, because the 4/6s being a little bit more of a special process to make, and then your long chains also being a little bit more expensive versus your short chain 6s, 6/6s and 6s, which if they can work for the application, great. And then we have these specialized 4/6s and 12s and 6/12s and 6/10s for applications that require their performance. But that would kind of be your ranking for it.
I think
We'll
it's
have
worth
to get back
noting
to
that,
them on UV.
for length of chain and UV or weatherability performance, there's long chain products that are out there that are used in constant outdoor exposure, and there's short chain products that are used for outdoor exposure constantly as well. So it's really a give and take of how the polymer is going to oxidize over time and whether that's sufficient for a given application. Um, so it's hard to say, yes, one's definitely better than the other. It's going to come down to the needs of a given part. And, we tend to choose the polymer that best fits that. But there are options for weatherable capabilities in both materials. So it might be a little tough to answer quickly, but how is nylon 6/6T made?
Yeah, so this would be kind of getting into the aromatic side of things. So anytime you see a material nylon base that's going to have either a T or a I in the nomenclature, that's referencing the type of acid that's being used. So a T is terephthalic acid, I being isophthalic acid. So you have a 6T, 6I, and then you have combinations of those, which are what makes our family of PPAs. So your amidels of the world. And so they use different combinations of that at a certain amount of those. How it's made is you remove, I don't have the polymerization way for it, but if you remove the linear section of carbons between the acids and you replace that with aromatic section, so benzene ring containing acids, isophthalic, terephthalic, I and T, and you replace those with those aromatic sections, that's how you then create your partially aromatic 6Ts, 6Is, and then any combination of that.
Good answer, Andrea. Next question, what would be the downside to having high water absorption in polyamides?
Well, there's a few things. One, the very first one that you'll encounter is going to be if it has a really high moisture absorption, you will have issues processing if it is not dried appropriately. So in the process of making nylons, water is given off as a byproduct. So if you put enough heat, it can start to go in the opposite direction. So if there's enough water or moisture present within the material, when you go to process it at the high temperatures, you can start to break up the chains. And so you'll end up with stuff like splay. You'll end up with chains that have been cut up. So you end up, it flows easier. And so you can have a lot of defects when you go to process it if it's not done correctly. And so that's one of the first issues you're going to encounter. The next one would be is if you are experiencing or the part is in a high humidity application, specifically in some of the ones that are a little more affected by moisture, you can see some potential swell and dimensional change. And so then you can have issues with if that part's being used or mating against something. If it swells, you might ruin whatever fit was being used there. And so quite a few different ways. Moisture really is kind of the biggest issue we run into with nylons. And so both from a processing perspective, if they're having issues processing it, and then resulting in defects when the parts are made, and then in application, if in a high humidity application or environment, you can see swelling of the part, which can interfere with what it's meant to be doing.
Jason, if I can interrupt, we had Harold raise his hand. So Harold, if you're still on the line, I'm going to unmute your mic and or try to unmute your mic. I'm going to see if this is going to let me do it. You may have to unmute your mic. If I sent you a request if you wanted to ask your question out loud, but if you want to do that and you can unmute your mic, go ahead and do that.
Can you hear me?
Yes.
Yeah, I don't know, maybe am I coming across too loud?
Nope.
No, you're fine.
Uh, the UV question is a real challenge because the pigment levels and the additives you have to put in today versus the past is a challenge because of the regulations. And what happens is you can destroy the properties of the resin. So that's why it's limited today and very challenging. But it can be done in certain colors, and that's why there's limited options today. And then, like you said, you can go to the other amorphous materials that have great UV.
For sure. Absolutely. Thank you. Yeah, it's if you start with a resin that, starts with great UV performance to begin with, it's easier then to either use as is or add even more or, just a little bit of a stabilizer to get to where you need to be versus a material that's, moderately okay at it and then having to add a bunch of stuff to it to get it to perform the way you need it to.
Thanks for the input, Harold. Next question, Andrea. Is there any new technology for lower yellowness index for natural nylon?
It's a good question. I'm not aware of any that, that they broadcasted. I would have to imagine that the main suppliers of this are working on that to make sure that one consistently getting, because that's could be, I don't know, an issue necessarily, but you get variation in the natural color quite a bit. And so I would imagine that the suppliers are consistently working on that to get a more consistent color out of it. Yellowing, not necessarily as much of an issue as I've heard. You get a lot more of issues with people using heat stabilized nylons, specifically if you're using a copper based one that tends to give it a greenish color. That could be a problem too. And so, but I would have to imagine, I've not been made aware of any very specific new discoveries in that area, but I would imagine our suppliers are working on it all the time. I'm sure they're getting complaints about it, so I'm sure that they're wanting to work on it all the time.
Next question here is, how does the usage of nylon 4,6 compare to acetal in overmolded gears?
Overmolded gears. So in general, when you're talking the wear performance of acetal versus 4,6, acetal actually at lower pressures and lower speeds will outperform a standard if we're just comparing straight standard unfilled, nothing's added, no PTFE, will actually outperform 4,6. But as soon as you start increasing the pressure or the velocity that you're using, which then will create more heat at the point of friction, 4,6 starts to become the leading material that you'd want to look at because the acetal cannot handle that. The other part of that is acetal is not great wearing on itself. And so if you're using any type or have any application, like maybe even the modular belting that I had a picture of, because that wears on itself, you wouldn't use acetal in an application like that. And then as soon as you start having just a little bit more speed, a little bit more pressure, you have to start looking at 4,6 to use instead of acetal because the acetal will not perform. It'll wear too quickly and get too hot.
Thanks, Andrea. Next question is, they admitted to maybe missing this, but is there a nylon that or polyamide that has a V0 rating, and are there flame retardant options in general, or are they flame retardant in general? I should say, rephrase that.
So nylon in general does not have the LOI, limited oxygen index, necessary to be inherently V0 or 5VA or inherently self-extinguishing, you should say. And so no, inherently it is not. However, you can make it V0 5VA by adding the necessary flame packages to it to achieve that.
All right, next question. Can you talk more about water absorption post molding? Parts may swell, but is strength affected?
It would be a little bit, yes. It would swell. Water tends to plasticize nylon as well. So it makes it more impact resistant, which is kind of nice. But in turn, then it would not be as strong and not be as stiff. So it could start to affect that as well. So if you're kind of right on the edge when you design with one of the materials, filled or unfilled, if it's going to be in an environment where it will see humidity and it will start to swell, pick up some moisture, you will start to lose some of its strength and stiffness. And so if it's right on the edge when you start to design for it or to make a part for it, there might need to be some considerations for a little more glass filler, maybe a stiffer material to start with, what have you, but it could be a potential issue. It's not going to shift, huge amounts, but it will shift.
Yeah, you'll see a greater degree of the change in mechanical performance based on moisture absorption in an unfilled material as opposed to like a glass fiber reinforced. But to Andrea's point, you are going to see a drop off in some aspects of performance in terms of, all modulus stiffness related values, flexural strength, tensile strength tend to decrease in a high humidity environment, which is why on many technical data sheets for polyamides, you see both dry and conditioned values, the conditioned values being there to primarily show the influence of moisture on them, so that when you're designing parts for use in a high humidity or high moisture environment, you can kind of cater which mechanical performance you'd like to measure by. It tends to be, if you're doing an FEA, for example, it's better to use conditioned values if you're anticipating a higher humidity environment to make sure that you're going to maintain sufficient strength or rigidity when exposed to said moisture. But thankfully, the majority of nylon manufacturers tend to get ahead of that on their data sheets and expectations for overall strength. Next question, I believe it might be the last one. Can the presence of splay in polyamide molded parts be used as a warning sign for possible mechanical property degradation due to moisture?
Yes. So if you're seeing visually that there's splay, it means that you're starting to break apart, could potentially be breaking apart the chains. And so that's going to affect its performance. And so as soon as you're seeing something like that, you should be looking into maybe drying procedures, what have you. But it could be a good first sign that there's probably something wrong and we need to address.
I think it's important to note, Adam, that this is more significant in nylons than in other materials because of their hygroscopic nature. That, if you were to see splay in a polycarbonate, for example, you would see it and know that there's moisture in the part in many cases, unless it's shear induced for some reason. But that's going to indicate a slight drop in mechanical performance in the polycarbonate. The problem gets much bigger with nylon as that moisture gets absorbed right into the chemical structure, into the polymer chain. And when the heat ultimately separates that water molecule, it separates the chain along with it. So the drop off in performance properties and mechanical is much greater in nylons for that reason when it's processed under a higher degree of moisture content. So yes, as Andrea said, is the short answer. It is a warning sign for drop off in mechanical performance.
All right, that looks like all of our questions. So this is going to be a wrap for us today. Thank you, Andrea and Jason, for giving us your expertise. And I'd like to thank all of you for attending the webinar today. And we look forward to seeing you at NPE in May. See you there.